Hello everyone, my name is Tiantian Ren. Today I will present our recent research work. The topic of our research is congestion analysis considering the management preference of decision makers in DEA. My presentation will consist of these 4 parts. Firstly, let me introduce the background and motivation of our research work. Economics of scale focus on the optimal size of a decision-making unit. When increasing the amount of input brings larger amount of output. However, there are many resources which affect the performance of a DMU when they are overused. This is known as congestion in economics literature. It is a widely observed phenomenon where the increase in inputs leads to the decrease in the optimal outputs. A typical example to explain congestion is that the overcrowding of miners in an underground mine, where the amount of mineral excavate will be decreased. In the original research, the concept of congestion will be developed based on the production function with single output. In practice, the real production function is often difficult to obtain, especially in multiple inputs and output production situation. DEA, as a data-driven evaluation method, can effectively approach the real production function. Therefore, a great deal of DEA literature has focused extensively on the analysis and applications of congestion. In these classic congestion studies under DEA framework, the basic idea for defining congestion can be summarized that the congested DMU has excessive inputs, that is, the target DMU evidence congestion if a reduction in its inputs leads to an increase in its optimal output. The corresponding models for mirror congestions of the target DMU is by searching for a reference unit with less inputs and more outputs than it from a specific production possible set. In essence, these conventional methods can be considered as concern the left-hand congestion of the target DMU. The left-hand congestion is interested in the change of optimal output of the target DMU caused by a reduction in its inputs. However, in fact, it is necessary for decision makers to consider not only the left-hand congestion but also the right-hand congestion. That is, an increase in inputs of the target DMU leads to a reduction in its optimal outputs. It is considered as the right-hand congestion in our work. In some situations, the DMU may only have the right-hand congestion but have no the left-hand congestion. However, the traditional methods will give a result that the DMU have no congestion. But this may mislead decision makers to continue to expand their inputs, which may bring congestion for production. Therefore, the right-hand congestion analysis have important management implications in real production, as it can help decision makers to determine whether they can continue to expand inputs and effectively avoid the negative impact on the production efficiency because of the over-investment. To the best of our knowledge, no reliable methods have yet been developed for identifying the right-hand congestion. This topic will be explored for the first time in our work. We aim at proposing a unified method to define the right-hand congestion and the left-hand congestion in DEA framework. Then, we will further focus on exploring a more detailed congestion classification to identify specific congestion status for the target DMU. This contribution is partly inspired by the original definitions of the strong and weak congestion proposed by Tong and Sehel in 2004, as well as the subsequent extension of this work. Different from the traditional classification of congestion, our multiple categories of congestion are defined by introducing the dominant relationship between the target DMU and its reference unit. Furthermore, in practical management, decision-makers have certain management preference for inputs and outputs. Take inputs as an example to explain this concept. The decision-maker usually has a desired strategy for adjusting different inputs with respect to the management needs. This can be described by a specific proportional relationship among these input increments. This relationship is referred as the management preference for inputs in our study. In this sense, what the decision maker really cares about is whether congestion will occur when the input is adjusted according to such a relationship. However, the traditional methods are not precise enough to answer these questions. Similarly, there are such a problem with output. So, building on our theoretical contributions mentioned above, we will develop the concept of directional congestion to identify congestion when the management preference of decision makers exists in real production. Our study aims to deal with about 3 issues on congestion. Now, with these issues, I will present the methodology part of our research. First, let us review one of the most widely used congestion definitions in DEA. It is proposed in Wei and Yan in 2004 and Tong and Sehel also in 2004. Their models referred to as the TS and WY methods. From definitions 2.1, we can find that it only focuses on the left-hand congestion for the target DMU. In fact, the logic of identifying the left-hand congestion is to transport the concept of congestion from a local framework to a global framework. In the whole P-convex, if there exists a reference unit which uses fewer inputs produce more outputs than the target DMU, this DMU evidences congestion. Therefore, definition 2.1 is referred to as the global left-hand congestion in our work. As mentioned earlier, the right-hand congestion analysis is also of great importance for management. In the following, we will explore the definitions and the properties of the right-hand congestion. Let us discuss whether it is feasible to define the right-hand congestion in a global way, similar to definitions 2.1. The global right-hand congestion can be defined as the underlying part, as we can see. However, These global definitions may bring the following two problems. We will explain these problems using Figure 3. One of the problems is that the reference unit is always formed due to the free disposability of outputs. Taking the DMU-A as an example, it is clear to find the DMU-B satisfy the conditions of the global right-hand congestion definitions. It indicates that DMU-A is congested according to the above global congestions. However, DMU-B is formed resulting from the free disposability assumption on outputs, which cannot imply that an increase in inputs of DMU-A will cause a decrease in its optimal outputs. It is possible for us to handle this problem if the region of finding the reference unit is limited to the frontier of the p-convex. But another problem will arise. That is a bias judgment of the target DMU. Also using DMU-A for explanation, DMU-C is located on the frontier of p-convex. It can be used to a reference unit to evidence that DMU-A is congested from the global congestion. However, it is obvious that DMU-A is not congested, but DMU-C is congested. Consequently, it is not feasible to define the right-hand congestion similar to the global left-hand congestion. Essentially, congestion describes the region of production function where the production declines as inputs increase. When discussing the definition of the right-hand congestion, it is necessary to ensure that both the target DMU and its reference unit are located on the frontier. Otherwise, the first problem will arise. In addition, congestion characterizes the local properties of an efficient DMU. If this point is ignored in the right-hand congestion, it will cause the second problem. With this classified, we propose the definitions of the right-hand congestion in a local way, and this way can be also applied to the left-hand congestion. In order to develop unified definitions between these two concepts, we consider the set phi to represent the strongly efficient frontier with respect to p-convex, corresponding to reset. The precise definitions of the left congestion and the right congestion are as definition 2.2 and 2.3. These local definitions effectively avoid the above two problems. In addition, the global definitions of left-hand congestion is equivalent to the local definitions of left-hand congestions, which is proved in our study. Then, based on the local definitions, we further explore a more detailed congestion classification to identify specific congestion status for the target DMU. Before this work, we find that the dominant relationship between the target DMU and its reference unit plays an important role in both the traditional congestion definitions and our proposed local definitions. To this end, the four categories of dominance are defined firstly in Pareto preference. that is, weak and weak dominance, strong and strong dominance, weak and strong dominance, and strong and weak dominance, which are expressed in definitions 2.4. Consequently, we can define the 4 categories of congestion based on the local left and right congestion definitions, respectively. For example, the left-hand weak and weak congestion can be defined as if and only if in a given state there exists a reference unit, weak and weakly dominates the target DMUs. Then, the left-hand strong and strong congestion, weak and strong congestion, and strong and weak congestion are defined similar. Conversely, the right-hand weak and weak congestion can be defined as if and only if in a given state there exists a reference unit satisfying the condition that the target DMU weak and weakly dominates the reference unit. It is noted that the 4 categories of contribution, that is, strong and strong, weak and strong, and strong and weak, imply weak and weak congestion. It is consistent of the traditional classification of congestion. In single input and single output case, there is no distinct among these 4 categories of congestion. These above theoretical contributions have made it clear that congestion characterizes the local properties of an efficient DMU. In the following, I am going to present another main contribution of our study. To evaluate congestion in a more practical context, we introduce the management preference of decision makers into the local definitions of congestion, which is essential for practical management. This part was explained in the introduction to the 3rd motivation of our work. To characterize the management preference of decision makers, we introduce the directions of inputs and outputs in our definitions of congestion. Then, the concept of directional congestion is further proposed as definition 3.1. From definition 3.1, the function beta t can be determined by solving this linear program. Then, our goal is to obtain the left derivative and the right derivative of beta t. The values of them can be applied to evaluate the left-hand and the right-hand congestion status of the target DMU in the given direction. With these notations, Theorem 4.1 is proposed to illustrate this in detail. From Theorem 4.1, if and only if the left derivative is less than 0, DMU evidences the left congestion in the given directions. Conversely, if and only if the right derivative is less than 0, the target DMU evidences right-hand congestion in the given directions. And then now we focus on computing the values of the left derivative and the right derivative. Therefore, theorem 4.2 is proposed. As we can see, theorem 4.2 provides a formula for calculating the left derivative and the right derivative. We have not shown the deduction of these above theorems in our presentation. It is worth mentioning that our method to measure the direction congestion is straightforward and requires no simplifying assumptions, which therefore can be extended to more general cases. Then, in the part of illustrated examples, we analyze an empirical dataset consisting of 6 basic research institutes in the CES in 2016. This dataset includes 2 inputs, research staff and research expenditures, and 3 outputs, external research funding, high SCI publications, graded patents. Our empirical analysis aims to achieve these 2 objectives. First, we illustrate how our method takes into account the right-hand congestion and the management preference of decision makers by comparing with TS and WY method. Second, by comparing with Mendelsohn's method, we further explore the benefit of the proposed method, which can consider any given management preference of decision makers. As we can see, Table 2 reports the results computed by TS and WY methods. Let us consider the evaluation results of DMU1 and DMU2. As we can observe, in Table 2, DMU1 evidences the left-hand congestion by using TS and WY method, but in fact, DMU1 has both left-hand and right-hand congestion in some input directions. This results of direction congestion indicates that, on the basis of existing inputs, if DMU1 decreases staff and expenditures in such proportions, can effectively eliminate congestion. In addition, DMU1 is not congested in some directions. Such results means that DMU1 can continue to expand their scale in the staff and expenditures according to these proportions, which will not bring congestion. Then, from the results of DMU2, no presence of congestion is found by using TS and WY method. This result only indicates that there is no left-hand congestion, as observed in column 4 in Table 4. This is the right-hand result provided by our method. We realize that DMU2 is suffering from the right-hand congestion in some input directions. In these cases, if DMU2 increases, staff and expenditures will lead to a decrease in outputs. Consequently, it is clear that managers are not suggested to extend the 2 inputs in these proportions. In the following, we turn to explore the benefits of the proposed method that can consider any given management preference of decision makers by comparing with Mendelsohn's method. It is Another typical method to recognize congestions. This method is shortly named as M's method in our research. Indeed, applying M's method to identifying congestion can be regarded as employing an implicit management preference, that is, an implicit input directions and output directions, and we can determine the implicit directions with the help of the target DMU and its non-congested benchmark, calculating by M's models. They are represented as the omega wave and delta wave. However, in actual management activities, the management preference of decision makers are always subjective, which may not necessarily correspond to the implicit directions determined by their models. For DMU1, assuming that the subjective management preference is to adjust staff and expenditures in an equal proportion and realize the improvement of the three outputs also in an equal proportion. In this case, the management preference is described in terms of equal changes in both input and output directions. From Table 3, we can find that it is non-congested in this direction. That is, the manager can continue to extend inputs under their current management preference. Consequently, our method over the traditional methods in precisely identifying the left-hand and right-hand congestion status for the target DMUs in any direction of inputs and outputs, which will provide more useful information to decision makers. In the last part, I am going to present the main conclusions of our study. Corresponding to the three research motivations present earlier, we use DEA methods to address these three issues as follows. Firstly, from the idea that congestion is a systemic and local concept, the unified definitions of the left congestion and right congestion in a local way are present. Secondly, based on the local congestion definitions, a more detailed congestion classification, that is, weak and weak congestion, strong and strong, weak and strong, and strong and weak, these four categories of congestion is proposed in our work. Thirdly, to address the issues of identifying congestion in a more practical context, the directional congestion is developed by combining the local congestion definitions with the management preference of decision makers. In the meanwhile, the empirical results indicate that the proposed method have advantages over the existing methods in precisely identifying the left-hand and right-hand congestion status for targeted DMUs in any given direction of inputs and outputs. Therefore, it will provide more useful additional information to decision makers, which is of important significance to the real management. Based on our current study, a possible future research is to take into account identifying directional congestion in the presence of undesirable outputs. In addition, another issue for future research is to extend these methods into some multiple-stage production situations. Thank you for listening to our presentation.